Right, this video is on understanding limits graphically and numerically. So limits are really important. We end up not having to do limits that often later, but the idea is super important. Okay, it's very, very, very important to understanding what's going on with all the things that we do in calculus. And so a lot of notation that we need to do. Now, a lot of this notation you may have done in pre-calc as switched into the calculus type notation, but we're still going to go over it carefully because it is important to read it. So we have the limit as x approaches c from the right. So this is a superscript of a plus sign of f of x, and that's how we would say that. So this is the limit as x approaches c from the right, okay, of f of x. But that's the way we would read that. So it's not a subscript, it is a superscript, and it doesn't mean that the number c is positive. Okay, it's saying it's from the right. Then we have the limit as x approaches c from the left. So that would be the same thing. The limit as x approaches, this would be c from the left. And then the general limit, we would just say the limit as x approaches c. And we're going to learn how you know when a limit exists. That's part of what we're going to do. So this is just the limit as x approaches c. So that's the general limit, okay? And so the left and right limits are going to be very important, and that's what we're going to sort of start to see when we go through this activity, because that helps us a little bit with the how we know a limit exists. Sometimes we have to look from both sides, because often the reason we're looking for a limit, so is this perfect example, we have a function and it has some places that are undefined. So often the limit is what can help us define those things, okay? So this is a rational function. So a rational function, hear this a lot, because if you understand that it's rational, there's a lot of features that it has the same. So there's a lot of things we know about it. So rational meaning polynomial over polynomial. So these are things that you studied in Algebra 2 and in pre-calc. And so we're just going to further use some ways to study it here. So one way that we can analyze the graph is that we can factor. So factoring is super important, used so much in calculus that it's really important that you can factor quickly. So I'm not going to review factoring right now on this video, but you should review it if you cannot factor it super fast. There should not be a bunch of intermediate steps. You should be able to get to these factors fairly quickly. If you can't, then you've got to practice. Now, when in Algebra 2, one thing that we do that's kind of bad, but we would just say, oh, cross that off, and this exactly equals 3x plus 1 over x plus 3. Well, that's not really true. It's super close. If you were to graph this function in your calculator, and then you were to graph this function in your calculator, they would look exactly the same, because in your calculator, you would not see this hole. So that's where, again, we have to know a little bit more than technology. We have to know there's not a point there, okay? There's a missing point at 3, and I know that because the original domain right here, even though I'm canceling them, I still need to say, oh, wait, but x can't be 3. This is only true, the equal sign is only true there if I further say, comma, x can't be 3. So they are equal everywhere except x equals 3. Well, the reason that's super relevant is if I want to know where this hole is. So I don't have a graph, I just have a function and I factored it, and I know there's a hole in the graph because of this that I could divide out. So I know, okay, there's a hole in the graph, right? So I need to find the coordinates. Well, obviously I can't plug it in to the original function because it's undefined. But what I can do is I can plug it into this function because they are identical except for the hole. That's the only difference. So in order to find the coordinates of the hole, all I have to do is actually just plug in to that simplified version of the function, which again is the same everywhere except at 3. So that value that I'm getting right here, which is 3, or is 5/3, is going to be my, because this is 10/6, which simplifies to 5/3, that's going to be the coordinates of my hole. Okay, so that's where the hole is. So if I graph it on the calculator, I could trace and then I could find the hole and so on, but we should already know when you can't divide by 0. So anything in the bottom that makes 0 causes me to have a hole or an asymptote if it's a rational function. Now the other thing that's missing, the -3 that I'm also can't have, right, because that would make that part 0, that's my vertical asymptote, and I can see that in this graph over here. So my domain are the x values that you're allowed. Well, in calculus, you need to be sure you're always using interval notation because you've got to be able to recognize it immediately when it's given to you, plus it's quicker in a lot of cases to write for different things, and so you'll see that. So I would be -infinity up to -3, and then parenthesis, because I can't include -3, union with -3 to 3, because everything in between -3 and 3 is fine. But again, at 3, I have a hole, so I can't use 3 and then to infinity. So that would be my domain. Now my range are my y values. So when you look at this range, you can see that there's a place right here that I don't have a value, which is at 3. That's the horizontal asymptote. But remember, I also don't have a value right here. So my y values, those two y values are not included. Everything else is. Notice the graph has arrows. So it covers everything else, just not those two values. So my range is going to be -infinity up to 5/3, which is the y value we found, union with 5/3 until we get to 3, because that's a horizontal asymptote that never crosses. And then I'm going to go 3 to infinity. So the range are your y values. Most of the time when we do range from a graph. It's a lot harder to figure out from a function. So most questions are usually you have a graph, or the range is obvious for other reasons. Okay, vertical asymptotes. Well, I can see it on the graph, and of course we know how to find it. That's when the bottom is 0 and the top is not 0. So that's the x plus 3 factor gives me the vertical asymptote. Asymptotes are lines, so it's x equals. Horizontal asymptote is y equals 3, and if you remember that, that's where you look at, you did this as Algebra 2 and pre-calc. Horizontal asymptotes for rational functions, you look at the highest powers, and you simplify that, and you'll get y equals 3. So there's my analysis of the graph using a little bit of limit notation. So now we're going to talk about how we would do limits and talk about them, changing them from the way we would have done it in pre-calc to the way we would do it in calculus. So for this graph, we're going to answer some things. So you have the graph sitting in front of you on your notes page. So I'm just going to answer these questions, and you look at your graph. I'll refer back occasionally. But in pre-calc, we might have said as x approaches -infinity, the graph of f of x approaches. That's what those arrows mean. But now we're just going to say the limit as x goes to -infinity of f of x equals, and we're going to say what we get. So if we go back and look at the graph, as we go to -infinity, that means I'm going this way. As I go that way, clearly the function is approaching the y value of 3. It's approaching that asymptote. Limits are a way to talk about what are we getting close to, not necessarily equal to. Might be equal, might not be, but that's what we're saying. So here's how we translate this one. The limit as x approaches infinity of f of x, and in rational functions, that's going to be the same value, and you can see that from the graph. as x approaches -3 from the right. So that's going to be written limit as x approaches -3 from the right, means I have a plus sign, and then I have to put the function f of x. Also notice that limit and f of x are on the same line, and the x approaches -3 from the right is a subscript underneath limit. So make sure that you're aware of that, and that you don't write your f of x in weird places, because I get students that write it in bizarre places. If this was a lined piece of paper, this would be your line on your paper, and they are level with each other. Now that answer, so as we approach -3 from the right, so when we talk about approaching from the right, we're literally talking about, here's -3 right here where this asymptote is, right? So I have to go on the right side of the graph and approach from the right. So that just means I'm over here and I'm following the graph and I'm coming towards -3 from the right. Well, what is the graph doing? Well, it's going to -infinity. So that's going to be my answer there. My answer is going to be -infinity. And that's okay. That's the answer. And then I'm going to also answer what is my limit as x approaches 3 from the left. So this is, I think that actually should, no, just approaches 3 from the left of f of x. Okay, so I look at 3, so I go back to my graph, and I approach 3, the number 3 from the left, so that means now I'm approaching this way, approaching the number 3, x equals 3 from the left. What am I approaching? In other words, what would be here if there was something there? And that is 5/3. So that answer will be 5/3. Okay, now let's, x approaches -3 from the left. So limit as x approaches -3 from the left. So I have a negative sign as a superscript here of f of x. Again, limit and f of x on the same line. X approaches -3 from the left is only under LIM, not under the whole entire expression. Okay, it's all under limit. That's one thing, and then f of x there. So as I approach -3 from the left, so looking at your graph, -3 is that asymptote, but now I'm approaching -3 from the left. So that means I'm on this part of the graph. I'm just traveling along the graph. I'm approaching from the left, and so I'm going to get positive infinity. And you don't have to write plus, you can just write infinity, or you can write plus. Doesn't matter. On positive, negative infinity, of course you have to say that. So now, as x approaches 3 from the right of f of x, okay, so from the right, well, if you look at your graph, from the right or the left is the same, they're both approaching that point. And so that's what 5/3 is. So there's a little thing here, and you can write down what you think this means in your words. I'm not going to write all of this out, but basically you should write out what you understand from what we just did. So the value of a limit in terms of a graph, the value of the limit is the y value that the graph is approaching from both the left and the right. It's, in other words, it's the target. It's what would be there, whether it's there or not. Okay, so the limit of this graph at 3 is 5/3, because that's what it is approaching. There's not a point there. There's no value there. It doesn't matter. There could be a value there. It'd still be the same answer. It's what am I approaching? Okay, what would be there? So it doesn't have to be there. So that's what the limit is talking about. Okay, so a limit is the y value which a function approaches, okay? Now, the important part that we're going to learn here is that the limit from the left and the right have to be the same in order for the limit to exist, and that's going to be the definition. So we're going to go through this next part. We're going to go through looking at this graph and answering quite a few of these. I'm going to go a little faster. This is a video. You can pause it, you can rewind, you can go back, but I'm going to go a little faster with this graph. We're going to use this different graph that's all over the place. This is clearly a piecewise function because there's a lot of different types of functions here all pieced together. And we're going to answer a bunch of questions. So over here I have it where we can see all of it. So we're going to answer these limits. Okay, so we're going to do it again a little quicker. And then you can just go back again and pause it, think about it, and so on. So first question is just what is f of 2? Well, this graph is called f of x, so this is the function of f. So f of 2 means just look at the graph and what's the value at 2. Well, that value is down here. It's not anywhere else. There's a dot there, so that's included. Up here, where there's an open circle, there's not a point. The value at 2, in order for this to be a function, I can't have two different values. So the value is defined down here. So f of 2 equals -1. Then f of -1. So I go to f of -1. Same kind of thing. There's no value here. The value's been redefined up there. So the answer for f of -1 is 4. Okay, it is not 2. There's no point there. Now let's talk about the limits as we approach some of those things, or some different things. So 3 says the limit as x approaches 4 from the left of f of x. So that means I'm on the graph and I'm approaching 4 from the left. So what am I approaching? The y is approaching 3. So that's the answer for the limit. Then the next one, limit as x approaches 2 from the right. So now I have to come at 2 from the right of 2. So this is the right side over here. So I'm coming this way. So what am I approaching? Well, I'm approaching 1. So that's the answer. There's not, the function value is not 1 right there, but the limit is. So the limit is what would be there. What am I approaching? If I got closer and closer and closer and closer and closer, what am I approaching? The next one says x approaches 2 from the left. Okay, x approaches 2 from the left. So coming from the left means I'm over here approaching 2. I'm following the graph. I'm approaching 2 from the left. Well, the answer from the left is -1. Okay, so in a minute, so we're going to actually skip to number, well, we'll skip to that in a minute. They're going to talk about what happens to the limit at 2. So let's go to F, or to, oh, sorry, 6, or F. On my paper it says F, so whatever yours says. The next one, x approaches -1 from the right. So if I'm approaching -1 from the right, so that means I'm right here, -1 from the right. My answer is 2. Then it says -1 from the left. So approaching from the left, also I get 2. Okay. Now 8, or I guess yours might say H. I don't know. My paper says H. The smartboard says 8. So whatever it is, limit as x approaches -4 from the right. So as I approach -4 from the right, and I'm going to use purple here, so I'm approaching -4 from the right, so I'm on the right side of -4, I'm approaching it, the y value is definitely 2. Now here's going to be a new one. The next one says approach -4 from the left. Well, guess what? There's nothing over here. There's no graph over here. The function isn't defined over there. I can't approach -4 from the left. So what we put here is does not exist, DNE. That is one of the few things that you should use to abbreviate. You could use DNE. That's a very common abbreviation. Do not put equals DNE, because you can't say the limit equals does not exist. That doesn't make sense. You're saying the limit doesn't exist and you're putting an equal sign. So don't put an equal sign, just put does not exist is the answer for that. And the reason it doesn't exist is there's nothing over there. I can't approach the graph from the left. There's nothing there. Next one says x approaches -1 in general. Okay, so what we look at is we're going to look at this one and this one. So as I approach -1 from the right, I got 2. As I approach -1 from the left, I got 2. So guess what the answer is? 2. That's the answer for approaching -1. The left and right limits are both 2, so the answer for the limit is 2. Now the next one says x approaches 2. So let's go back to where we did x approaches 2. From the right we got 1, from the left we got -1. So therefore this one does not exist because the left and right limits are different. If you are approaching this graph, you're coming from both directions, you're getting two completely different things. So there is no limit at 2. So there's a reason for a limit to not exist. limit as x approaches 5. This is just going to be if this was continuing, this just continues on, right? There's an arrow there. So if the function is defined and there's a point there and the graph exists on both sides, then that's the answer. So as I approach 5, my answer is just -2. So same thing with 0. As x approaches 0, I just have a value. The graph is defined on both sides of it. So I have an exact answer, which is -1. And then as x approaches 1, same thing, the answer is just -2. So when graphs are defined and there's something on both sides, we're all good, okay? So at the bottom of that statement, they talk about, you have it in front of you, I'm gonna look at the graph. So it says to think about this. Think of the function as a highway. If you look at the point 2, -1, that's like the end of the road. So if I'm driving on this highway and I'm going along this highway and then I hit right here, the road just ended. So done. So it just stopped. So that's a dead end that has a barrier on it. We're just done. The point -1, 2, though, different. This hole that was over here, you can think of that like a pothole. If I was driving on this road, I could drive on this road and I could go over that pothole and keep going. So that's the reason that holes are what we call removable discontinuities. I could redefine the function to fill that hole in and it would become continuous. This discontinuity, so it's a little foreshadowing for stuff later, definitely I can't fix that because without changing the entire function. I can't move the graph until those meet or I've changed everything. So looking at the point 2, 1, we would call that like a dead end that has no barrier. So this would be driving on the road, and oh, the bridge is out. Well, I got to stop anyway because I'm going to fall off the road. So I still have an ending, still have to stop there. And then 4, 3 is kind of like a bump in the road, like, oh, I got to make a sharp turn and I got to go this way. And those are important features of the graphs that you'll see later. Okay, so let's talk about when limits don't exist. So here's a graph, case 1. Here's a reason the limits don't exist. So the limit doesn't exist for this function, which is x, absolute value of x plus 1 over x plus 1. So the reason this one doesn't exist is because the limit as x approaches -1 from the right of the function f of x. So if I'm on the right side, I'm on the top portion of that, the limit is 1. If I do the limit as x approaches -1 from the left of the function, I'm going to get -1. And so therefore, since these two things do not equal each other, the limit is x. Here's how I would explain it in math, and you're going to need to learn to explain in math now that we're in calculus. Here's my math explanation, okay, is that these two limits are not equal. And if they don't equal each other, this is the reason it doesn't exist. So the left and right limits differ. So this is why this one doesn't exist. The left and right limits are not the same. Now this graph, it's hard to see on here. This is a fun one you might graph on your calculator. But clearly, we're looking at what's happening at 0. Well, definitely, there's no graph at 0, right? So it's undefined. Well, if you graph this in your calculator and just keep zooming in and zooming in and zooming in, it's kind of a fun one to look at. It's just going to keep going up, down, up, down, up, down, up, down, up, down, up, down. And so you're going to end up having it not exist because we have what we call oscillating behavior. Okay, so it's oscillating. And so I cannot get an answer because every time I keep trying to move closer to 0, it jumps up and then it jumps down. It doesn't matter if I'm on the right or left. It just keeps going up and down, up and down, up and down. It's oscillating. Okay, so that's what we call that. And then our third case is the reason the limit does not exist here is because the limit is from the left and right. So if I do the limit as x approaches 2 from the right of this function, I get infinity. If I do limit as x approaches 2 from the left of the function, I get infinity. And I can actually say that the limit as x approaches 2 of f of x is infinity, but by definition, that would mean it doesn't exist. Okay, so this is another reason it doesn't exist, because this is not a real number. For a limit to exist, we need to have a real number. So we call this unbounded. Okay, so your behavior at the place you're looking is unbounded. So this one's just going to infinity, which also means it doesn't exist. Okay, so now let's get into this. Now, this is something you can do on your calculator. I'm just going to fill these in really quickly so you can see what's happening. So if you did this on the calculator, which is a good exercise, if you're not really fast with your calculator, I would suggest doing this because you need to get quick with your calculator in calculus. We do a lot of stuff with the calculator. If I were just to plug in these values into this function right here, so I just plug them in, these are the values that I would get. So basically here we're approaching 3 from the left, here we're approaching 3 from the right. The value at 3 is undefined, which is often the reason that we want to answer the question of the limit is because we don't have a value, and so we're trying to find it. So as we approach from the left and the right, though, we get the same answer. We can see that it appears to be 0.125, and so then we would believe that the limit is in fact 0.125 at 3. So not having a point there doesn't affect having the limit. So this is a good picture. You can read that about that. A limit doesn't have to be there in order for it to happen. So the limit existence theorem says that the limit as x approaches c of f of x exists if and only if the limit as x approaches c from the left of f of x equals the limit as x approaches c from the right of f of x, which equals L, where L is a real number. In other words, you have to get an actual number answer. If you get a number answer, then the limit exists, and the limit is that value. If it doesn't, then we don't. So basically, we usually just say approaches from the left and the right. If they're the same and they're a value, then the limit exists, and that's what the limit is. So that is your introduction to limits, and the rest will be done in class. And then we'll do more